Hello everyone, good afternoon, good evening, good morning from wherever you are. My name is Ying and I will co-host today's event together with Dr. Nagham Saeed. I would like to welcome our audience and speakers to our 13th Early Career Talks event, which is one of our IEEE UK and Ireland Women in Engineering activities. For this 13th Early Career Talks, we are focusing on the topic of unlocking the potential of offshore renewable energy, innovations, challenges, and environmental sustainability. We plan to have 4 distinguished speakers to talk about the power and control, Internet of Underwater Things, protection for HVDC, EMC in power electronics. Here is the agenda for today's event. Firstly, I would like to mention that the presentation recording will be broadcast on our IEEE section website and our YouTube channel. We will take questions from the audience after each presentation. Please provide your email in the evaluation form, which I will share later at the end of this event. And if you want to receive your e-certificate, please do provide your email and your feedback. Before we start, here are some housekeeping notes. You will notice that you are muted and you can't use your camera. If you have any questions that occur to you during the talk and you don't want to lose track of, please do type them into our Q&A chat box and we can address those at the end. To target the questions to the right speaker, please write with the question with the speaker's name or their talk order. We will try to answer the questions at the end of each presentation. Now, I will hand over to our first speaker, Dr. Yuchao Liu from Northumbria University.
Thank you, Ying, for the introduction. So let me quickly share my screen first.
Yes, please.
Can you see my screen?
Good.
Yeah, okay. So everybody can hear me clearly?
Good here.
Great, thank you very much. Okay, so thank you for the invitation for the 13th Early Career Talk for the IEEE Women in Engineering. So today I'm going to talk about multi-terminal HVDC and undersea pumped hydro energy storage for offshore wind farms. So first, I would like to introduce myself briefly. So at the moment, I'm a lecturer at Northumbria University. So I joined Northumbria University in the Department of Mathematics, Physics, and Electrical Engineering in January 2023. So before I joined Northumbria, I was a research fellow in the Power Electronics, Machines and Control Research Group at the University of Nottingham. So my research interests include power converters and control, multi-terminal DC transmission, and integration of renewable energies. First, I would like to give a brief introduction about the offshore wind in the UK. So, as you may know, the UK government is committed to quadruple offshore wind, which is 50 gigawatt by 2030. As you can see today, so the UK have installed offshore wind capacity, which is 13.7 gigawatts. So by 2030, it's increased like 265%. So this is as a cornerstone of its goal to fully decarbonize electricity by 2030. By 2050, sorry. Delivering the huge expansion in offshore wind will require change and therefore bring some challenges to the UK's power network system. So multi-terminal HVDC and undersea pumped hydro energy storage are two promising technologies to help balance the power supply and demand, improve the stability and flexibility of offshore wind farms. So compared to the traditional Hello. I think.
Yeah, can you please share again? Sorry, something happened. Yeah.
Something happened. Yeah.
Yes.
I know. Okay. Okay. One sec. How about now?
Good now.
Yes, we can see now. Thank you.
Sorry about that. I think probably we have some internet issues. Okay. So compared to the traditional HVAC transmission, so HVDC has a lower power losses. As you can see, traditional HVAC, you need lots of overhead transmission lines. But for the HVDC, you may need underground cables and submarine cables, which is much lighter. And even for the HVDC light, so everything is underground, which reduce the footprint platforms. And also another reason, as the transmission line length increasing, for example, from 700 kilometers to 3,000 kilometers, the AC transmission capacity is reduced heavily. So, for example, for almost 50% compensation. So, based on that, so over a certain distance of the transmission, so the investment cost of the DC transmission is lower than the AC transmission. So therefore, we know most of the offshore wind farm is quite remote from the main grid and also the consumers. Therefore, the HVDC transmission is more suitable for offshore wind farm integration. This is a very traditional point-to-point offshore power transmission system. As you can see, we built up the offshore wind farms and use submarine AC cables, go through a HVDC station, which is AC to DC, and then through a submarine DC cable and to another HVDC, which is a station, which is DC to AC transmission, and then go through the overhead lines and go to the urban consumers or power grid. So as you can see here, the most important part is the HVDC stations. So nowadays, we mainly use voltage source converters. So based on the voltage source converters, so the HVDC power transmission has a lower filtering requirements. It's much lighter weight and saving the platform footprint. And also because it's based on the voltage source converter, it do not rely on very strong AC grid and can provide reactive power support to your wind farms. And this one is also easy to power reverse, so which means you can easily to expand or integrate to other renewable systems, resources, or the storage systems. And this has the black starting of a offshore wind farm. So based on the point-to-point HVDC transmission, so this is the concept of the multi-terminal HVDC transmission. As you can see from this, this is a typical multi-terminal VSC HVDC-based offshore wind farm integration system. As you can see, we can connect multiple offshore wind farm. So, and then we connect it, and then we can supply for the offshore load, and also we can transmit the wind farm power through the submarine cables to connect to the onshore power grid. The onshore VSC HVDC stations also connect to the existing power grid and also send power to the consumers. So the MTDC has a higher flexibility and scalability, higher reliability and stability, and also has efficient long distance transmissions, so which make it very easy to integrate with other renewable energy sources, for example, solar PV. and also in the wave energy. So, and this can provide us the facilitating energy storage integration. And also, because this is very easy to expand, so, and has the redundant and flexible flexibility, which enable the massive integration of offshore wind power in the future power system. So also has a lower overall infrastructure cost. So also we know MTDC is a promising technology for the offshore wind farm, but also we have meet lots of challenges for the offshore wind farm. For example, as we know, the wind farm has lots of uncertainties. So the investment in the electricity grid are not keeping pace with offshore wind installation. So as such, offshore wind curtailment costs are rising for the energy system operator, which is the national grid ESO. So under the current market mechanism, so when there's a thermal network constraint due to the excess levels of wind generation, the national grid ESO will pay for the curtailment of wind to manage the constraint. So under the constraint condition, so ESO have to pay the curtailment wind farm curtailment to curtail the wind farm output, which means the national grid ESO need to pay extra money for the wind farm companies to switch off the wind turbine or wind output. Even the wind turbine may still operating, but it's not connected to the main grid. It's not being used. So, which means the wind constraint cost reduction is one of the biggest challenge for the national grid ESO. So in 2022, the UK spent about 250 million on turning wind farms off, and another 717 million to turning on the gas power plants to replace the lost wind power, which means it emitted an extra 1.5 million tons CO2. So this is one of the challenges, and also another challenge is the integration with the existing infrastructure. So also we have another challenge about energy storage systems. To trying to reduce the wind constraint cost reduction, I think energy storage systems, particularly the long-term energy storage system, will play a critical enabling role in improving the system resilience and economic benefits in the offshore grid integration. So the main aims and motivation for this research is trying to use the co-locate long duration storage with the existing offshore wind farm to reduce the curtailment cost from the offshore wind. Okay, from the published from the Royal Society, there's a publication. So UK have to explore a big long duration storage to trying to facilitate the big offshore wind farm installations. So by that we have like the aim for 100 terawatt of the storage. So for this big expansion of storage, is obviously the current traditional battery storage technology is not sufficient. It's not enough for this. So which makes us to need to explore for new storage technologies. So for one of the aim is trying to explore the barriers for co-locating storage with offshore wind, monitoring and balancing the mechanism. And also use the multi-terminal HVDC network connecting wind generation and storage to reduce the number of individual connections to the UK grid, which can make the whole power net system more flexible. So as one like storage options, hydrogen, I think has attracted lots of attentions for the storage. However, the hydrogen round trip efficiency is around 30%. So notwithstanding challenges around transportation of hydrogen, so there's an opportunity for alternative long-duration energy storage technologies to meet expected need. So my main research area, the target is trying to integrate multiple wind farms to the existing multiple support the grid, trying to create an economic, flexible, reliable, and stable power network. So based on this target, so there are two research main topics. The first one is the power converter to interface between the wind farms, storage, and the grid. As you can see, every two terminals, we need to use the power converter, either AC-DC, DC-AC, or DC-DC converters. So another one is the multi-terminal HVDC power coordinate control to provide power flow management, fault current contribution, inertia, frequency response, and voltage stabilities. So during my previous research, previously we built a 6-terminal VSC laboratory platform, which is around 700 volts, 30 kilowatt. So, so we can use the 6 voltage source converter to trying to explore, investigate the different topologies for the integrate offshore wind farm. For example, star topologies, ring topologies, and so on. And also we did some experiments based on the multi-terminal HVDC. So one of the most important presample for MTDC is the N-1 presample, which means at any time, any one terminal, any one farm or grid stop operating, so the rest of the power system, the MTDC will still keep operating. For example, for this one, so here, when one of the wind farms stopped operating, as you can see, after like few milliseconds, so the whole system reached a new balance, new stable operations mode, because one of the wind farms stops operating, so the power supply reduced, which caused the DC voltage a drop. However, so they start to reach a new balanced operation mode. And so for the undersea pumped hydro energy storage, so the idea is trying to use 3D printing to create a concrete sphere. So the sphere. So the sphere is normally placed on the sea floor. So on the sea floor, so this is the charging and discharging of the pumped hydro energy storage system. So initially the sphere is filled with water and placed on the sea floor. So when there's surplus energy from the wind farm, so the excess energy is used to pump. So to pump the water outside from the sphere into the sea, which we can store the energy into the sphere. Similarly, so similarly, when there's low wind and high like power demand, so we can use the pressure from the sea to pump the to let the water flow in from the sea into the sphere, so through the turbine, which can like transfer into electricity. So for here, as you can see, this is a reversible pump turbine unit, and this is a steel pipe, which will allow the water flow in and out of the sphere. So as you can see, this one, this is the offshore wind farm with the pumped hydro energy storage system. So any excess of the energy can drive in the pump and to store the electricity into the sphere. But however, then when the wind farm is in a low supply, but there's a high demand for the grid or the load, so then the water can flow into the sphere to drive in the turbine to generate electricity. Okay, this is we did some simulation for this hydro pump for this like offshore wind farm MTDC system with pumped hydro energy storage system. So this is the simulation result and low wind speed. So as you can see, when the wind is very low, so we normally switch off the wind power plants, wind turbines. And so the energy supplied by the storage system to the grid at a lower wind speed. So the output of the powers of storage system is based on the demand of the load and the grid. So this is the voltage, transmission voltage, and the current for the MTDC system. As we can see, even we switch off the wind turbines based on this storage system, so the grid can still maintain a stable operation condition. So this is the simulation result and the variable wind speed. So as you can see, this is the charging and discharging mode of the pumped hydro energy storage system. So it's based on the demand and the wind turbine output. So the storage system is working on the charging and discharging mode. And as you can see, this is the AC output waveform of the grid system. So by using the energy storage system can help the whole system to work in a more stable condition. So the conclusion, so multi-terminal HVDC transmission with energy storage system is a feasible and sustainable solution for integrating large-scale offshore wind farms. So by co-locating the wind farm and the energy storage could reduce the wind stream cost, so which can help to reduce the cost for the curtailment for national grid ESO. And identify and provide solutions to the market barriers for long-duration energy storage to co-locate with offshore wind generation. So based on the pumped hydro energy storage system, it depends on the size and also the number of the sphere. So it can like reach a 300 megawatt hour storage capacity as maximum up to like 30 hours duration storage. So this can also help to unlock whole system benefits of the non-duration energy storage coupled with offshore wind farm. Okay, that's my main presentation. Thank you very much.
Thank you, Yuchao. Thank you for the informative presentation. So let's see if there is any question from our audience. Yes. Thank you, Ruhul. Ruhul, do you have a question?
Yes, I have one question.
Please.
It's a short one. Since the presentation was really outstanding and it was like in a very detailed. First of all, I would like to thank you, for this very good presentation. I have like one short question, which I would like to ask that. Since it's not my research area, but a short general question which comes to my mind is that how this multi-terminal HVDC work for like different kind of losses, for example, the filter loss, in which we can like consider the harmonics, how it basically give us the smooth harmonics. And the second is like how it works for the auxiliary power losses. So like in case of power losses, how it works as compared to the AC or the normal HVDC.
Oh, sorry. Can I confirm the question? The first question is like the harmonic. Is that what you mean?
Yes, because usually the multi-terminal HVDC transmitter gives much more smoother, you can say harmonics as compared to the normal AC and the simple HVDC, point-to-point HVDC we call it as well. So my question is that how it will basically come up with it very smooth as compared to them.
Very small. Sorry, can you very small? I missed the one point from you. So how about the last sentence? Very small. Sorry.
My question is that how it basically gives us smooth harmonics as compared to the normal AC and point-to-point HVDC.
Okay, yeah. So basically, actually, as you said, for the multi-terminal HVDC, we used, for example, MMC. So if you have used like multi-levels, so the harmonic is really low. We don't need any like filter systems, which is one of the advantages for MTDC compared to the traditional HVAC system. So
yeah, thank you very much for
yeah.
the detailed answer. Thank you very much.
Mm-hmm.
Thank
So
you.
the second question. So sorry. Can you repeat your second question, please?
Hi, Ruhul.
I think if
The
Rahul
second
just
question,
write it, sorry about that, Rahul, if you just write it for her in our chat and
no,
she
please
will
go
reply
ahead.
to you so we can go.
It's all right.
Thank you very much.
Yeah,
Thanks.
please go ahead. Please go ahead.
So because of the time limitation,
Mm-hmm.
yes. So if you have any other questions for our first speaker, please type your question in our Q&A chat box, and our speaker will try to answer it there as well. Now I will
Thank you very much. Mm-hmm.
Thank you. Now I will hand over to our next speaker, Dr. Ruhul Amin Khalil from United Arab Emirates University.
Hello, everyone. My name is Ruhul Amin Khalil. I'm a postdoctoral research fellow at the United Arab Emirates University, specializing in underwater wireless communication. First of all, thank you very much to the IEEE UK team for inviting me to speak at the 13th Earlier Career Talks. The topic I will be discussing is navigating the depths innovation in the Internet of Underwater Things. This is basically a field that is rapidly evolving and holds immense potential for various applications, from environmental monitoring to military applications and underwater navigation and so on. My talk will cover the latest research, current challenges, and future directions in this fascinating area. Let me start by giving you a brief introduction to my background. I am currently working as a postdoctoral research fellow at the United Arab Emirates University. I have been working as a lecturer at the University of Engineering and Technology, Peshawar, Pakistan since 2013. With PhD in electrical engineering, my focus has been on underwater wireless communication. Over the past 11 years, I have accumulated extensive research experience in both academia and research, publishing more than 36 journals and 8 conference publications. My contributions to the field have been recognized by IEEE, the Consumers Electronics Society, where I received the Best Research Award in 2021. And most recently, I was honored with the Best Researcher recognition by the UAE University in 2024. Okay, let's talk about the Internet of Underwater Things, or simply called as IOUT, is a network of smart interconnected underwater devices such as sensors, vehicles, and various other objects. These devices are designed to collect and transmit data using different communication technologies like acoustic, optical, and magnetic induction. The significance of IOUT extends across multiple fields. It plays a crucial role in underwater exploration, environmental monitoring,
disaster prevention. It is used for scientific research and even military applications as well. As we advance, these interconnected systems will continue to push the boundaries of what's possible in underwater environment. Our research area is basically positioning and localization in Internet of Underwater Things. Accurate positioning and localization are basically very critical for the effectiveness of IOUT networks. In underwater environments, challenges like signal attenuation, multipath effect makes this task particularly difficult. However, with the advancement in positioning techniques, we can now more precisely determine the location of underwater devices or any other objects which is unknown in the vicinity. This is essential for applications such as tracking underwater vehicles, monitoring marine life, and ensuring the safety of offshore infrastructure. The illustration on the slide demonstrates how positioning and localization are implemented within IOUT network. These network can consist of different devices. For example, they can use the acoustic link, or for offshore communication, we require the radio frequency communication. As discussed in the previous slide, we use different communication mediums in the IOUT networks. There are three primarily communication mediums which I would like to discuss in the IOUT network. That includes acoustic, optical, magnetic induction. Acoustic communication is mostly used due to its long-range capability, although it has limitations such as low data rate, susceptibility to multipath effects. Optical communication, on the other hand, offers higher data rates and low latency, but it is limited by its short range and high absorption in underwater environment. Lastly, the magnetic induction communication is much more effective as compared to the optical and acoustic, but they have a short range application. But on the other side, it offers robust signal penetration and low power consumption, and it has no effect on the marine life as well as compared to the acoustic, where the many marine life creatures communicate with each other through acoustic communication and optical as well. Each of these three medium has its specific applications depending on the requirements and condition of underwater environment. Here we will discuss some of the current methods for positioning in the Internet of Underwater Things network. We explore the various methods using for positioning within IOUT network. Techniques like GPS, time of arrival, time difference of arrival, angle of arrival, and receive signal strength are commonly adopted for underwater use despite their inherent challenges. For instance, while GPS is not directly applicable in underwater environment, so hybrid method that combines the time of arrival and angle of arrival or the received signal strength can significantly improve the positioning accuracy. Additionally, advanced techniques such as Bayesian estimation, Kalman filtering, and signal of opportunity. The signal of opportunity is the one we usually explore in our research area, and we'll discuss it later on. Approaches are being developed to enhance the reliability and precision of underwater localization, or you can simply call it as positioning. Here I will be discussing one of our case study that we did during our research journey. Is basically we are interested in positioning of the hybrid Internet of Underwater thing. This case study focuses on positioning within hybrid Internet of Underwater networks, which demand high data rates, low latency, and long-range network capabilities. In our research, we introduced a signal of opportunity approach based on hybrid approach that consider acoustic, optical, magnetic induction ranging, whichever is available and can be utilized. We then used multidimensional scaling with precursus analysis. We were able to estimate the positions of IOUT devices with greater accuracy. Additionally, we performed the Kramer-Rao lower bound analysis, which basically validated the effectiveness of our proposed method. This slide shows the different components, the sensors, and the different communication devices in the underwater environment. If you have a look, there are some sensors lying on the surface of the seabed and then they communicate with each other either on the optical link, either acoustic link, or either magnetic induction because they are nearer to each other. Then we are having the submarines, which usually communicate with the help of acoustic links, and then we have an anchor node, which are basically the surface buoys on the surface, and then we communicate with the offshore communication through an RF link. So it is basically a combination of a hybrid network, which is based on the signal of opportunity approach that includes, if any medium is available, the system can accommodate that and can utilize that for the positioning purpose. This slide shows the two scenarios where we consider a 100 by 100 by 100 three-dimensional area, where we, in the first case, we introduce 50 sparsely distributed nodes, and in the second scenario, we consider the 100 densely distributed nodes. We have 4 anchor nodes, which are represented by the black square, if you can see that on the each corner side. So their positions are known to us, and based on these anchor nodes, we can measure the position of the unknown nodes. So in the first case, we sparsely distributed 50 nodes, and we estimated the position according to the scenario considered relative to the anchor nodes, and then we compare it with their actual position. So there is a very less error in that, right? And on the other hand, if the number of nodes are increased, in the second case, we consider 100 densely distributed nodes. So the results are much more better, because if the number of nodes increases, the accuracy also increases. We'll discuss it in the next slide, where we discuss the different results obtained while considering these two scenarios. This slide shows some of the results we obtained while considering the scenarios for the 50 sparsely distributed sensors and for the 100 densely distributed sensors. The figures illustrate various aspects of our approach. The first one includes the impact of ranging noise variance, that how RMSE changes with respect to the change in the noise variance. The effect of increasing number of anchor nodes, how the RMSE root mean square error changes with respect to the increase in number of anchor nodes. For some time it might decreases, but after if you can see from after 14, it becomes unchanged, and no matter how many anchors you can change or increase, it will have no effect on the RMSE. The third one shows basically the relationship between the energy error product and the transmission range. With the increase in the transmission range, the energy error product increases, right? Overall, finding indicates that the proposed method not only improves accuracy, but also enhances the overall efficiency of the IOUT system, making it promising solution for the future applications. In the previous cases, we only consider the traditional underwater networks. What if the integrated sensing and communication based IoT networks are available? So the integrated sensing and communication, which is simply called as ISIC, is nowadays an innovative approach that combines the sensing and communication functionalities into a single system, whether that is an IoT network or that is a terrestrial network or aerial network. This integration offers several benefits, including increased resources efficiency, reduced latency, and significant energy savings. Recent advancements in ISIC for IOUT network include the development of hybrid systems that combine acoustic and optical methods, the use of machine learning to improve signal processing, and creation of multifunctional devices that integrate sensors and communication modules into compact units. Additionally, energy harvesting techniques are also being explored to power these systems using renewable resources, enabling autonomous long-term operations. Currently, we are working on the positioning and localization in the ISIC-based IOUT networks. We have developed an efficient asynchronous localization method that addresses challenges such as propagation delays and mobility. This method employs an iterative least square approach for the precise localization of autonomous underwater vehicles, and incorporate a mobility model for further refinement. Additionally, we have introduced a novel pre-coding design scheme that optimizes data transmission, leading to improved position estimation, accuracy, and enhanced sensing efficacy. As demonstrated by our Monte Carlo simulation, our results are much better as compared to the traditional techniques. So we are currently working on that and enhancing those techniques. Here are some future research directions and challenges in IIoT networks. As we look to future, several emerging trends will shape the development of IIoT networks. Advancements in sensing technologies are enabling the creation of more durable and energy-efficient sensors. The integration of AI and machine learning, as discussed, is improving data analysis, predictive maintenance, and autonomous decision-making. Hybrid communication, on the other hand, are being developed to optimize data transmission across different mediums, while energy harvesting solutions are being implemented to power IoT devices using renewable resources. However, several challenges are still there and require much attention to be solved, including communication reliability, energy management, data security, scalability, and minimizing environmental impact. The ongoing research and collaboration are essential to address these challenges and unlock the full potential of IoT networks. Okay, here are some of the conclusions, the things we discussed in this presentation. To conclude, this presentation has highlighted key innovations and applications within the IoT networks, focusing on advancement in sensing and communication. As we discussed, various localization techniques emphasizing their strengths, practical applications in underwater environment. The significance of ISIC-based IoT network underscore along with recent advancement in the field. Finally, we have emphasized on the importance of ongoing research to further enhance the IoT technologies by understanding their environmental impacts and expand their real-world applications. This slide listed some of the recent publications in this area, which I shared here. You are more than welcome to study them, and if there is any discussion you would like to take, please do not hesitate to reach me out. Thank you very much for your attention, and I'm happy to take any questions you may have. Thank you very much.
Our next speaker, in our plan, I think our next speaker is Fatima from GE, but unfortunately, she encountered an emergency situation, so she cannot join us today. So let's move to our last speaker, Arun, from the University of Nottingham. Over to you, Arun.
All right. Let me actually show my. Can I share my screen?
Yes, please.
My screen, so you can actually, or I'll share the Microsoft PowerPoint. So go share.
Oh, okay. Oh yeah, you can share now.
Yes. So here, can you see my presentation now, or?
Yes, now we can see it.
Yeah. Okay. Let me. Yeah. Is it okay? Can you all see my screen?
Yeah.
Yes.
All right. So I'll begin. Okay. All right. Well, thank you first of all to the organizers for including me on this panel for early career talks. My research is about EMC in HVDC grids and converter applications. It's quite a new topic, so I'll introduce a very high level of talk of EMC in HVDC because it's not something that has been researched up till now, but we are now trying to find more avenues towards researching EMC in DC. I will also explain what EMC is for the audience. So to start with my introduction, I now have recently got a PhD in electromagnetic compatibility from the University of Nottingham. I recently graduated with the degree. I got my master's degree in electrical power engineering from Chalmers University of Technology in Sweden in 2019, and then I migrated to the UK to get a PhD at the University of Nottingham. Then I got a bachelor's degree in electrical engineering from the University of Mumbai, which is my home country, from 2009. And I've got also over 6 years of industrial experience. That means I had worked in HVDC projects. I had worked in water treatment plants. I had worked in a whole lot of industries which required electrical engineering design. But today I'll be speaking to you about my research in EMC, which is applied in power electronics in HVDC. Okay. So on your left on the screen, you can see there's a very picturesque map of what looks like a part of the global grid. That means all of in the near future or in the coming decades, we might achieve a level of electricity generation, consumption, and transmission which spans across countries with different types of generation plants, all linked through HVDC links. So these generation plants can be photovoltaics, wind energy, hydro energy, biomass, geothermal, all of these links from different power plants, all of them linked in one big network of HVDC links. And mind you, it's DC link and not AC link. They might have HVAC, but usually we are looking at HVDC links. But in the future, this is the hypothesis that we are actually right now working on, because that's the electrical future of the world we would like to see. So we already have a lot of interconnections between countries. Right now, even the UK takes a lot of power from Norway and from France, and then from other neighboring countries, from Scotland as well. With England also takes power from Scotland and the reservoirs there, and all of these are interconnected by HVDC power electronics. My colleagues have already explained what HVDC power electronics are, so let me not go into the details of power electronics of HVDC power electronics. Let me just maintain what EMC would be in power electronics. So what happens is when you have all these links interconnected with HVDC within different countries, or within countries that are very neighboring countries to each other as well, all this results in too much electrical noise. And that electrical noise in technical terms is called EMC. So EMC is basically understanding electrical noise in HVDC links. So what happens is when you have such a scenario where a lot of countries are exchanging power, the delivered power quality becomes an issue. So suppose tomorrow you're charging your car here in Nottingham in the UK, and my power is coming in from, say, Denmark, and from Denmark it's coming to London it's coming to Nottingham. So I'm purchasing power from the Denmark, but I have a stringent requirement or a grid code that my power quality for DC has to be a certain level, and for power quality to be what it is, it has to have a lower level of electrical noise, which means it has to have a lot of which means it has to have a decent amount of EMC, which is electromagnetic compatibility, a rather technical term for what we call as electrical noise. But right now in the world, there are no standards or frameworks to understand what EMC would look for in DC. We have enough understanding with AC. You might have heard terms like total harmonic distortion in AC, but you haven't heard anything like that in DC yet, because it's not researched yet. And now we are heading towards a world where everything is more DC, and we need standards and framework for DC, which I will also explain further going into my presentation. Okay. So, but again, let me now explain what, in simplest terms, is EMC and HVDC, like what electromagnetic compatibility actually is. So what is electrical noise or EMC? Suppose you have a sine wave, which we all are very familiar with. It's simply 230 volts, which goes back and forth into your system, powers up the entire world, good and well. But when it's actually coming into your electrical grid, it's distorted. Okay, like this. This is the actual power which we actually consume, and you can see the distortion will have an index to it, and that index is known as power quality. So the more distorted it is, the worse the worse the power quality of electrical AC generation. That means the power quality is below a certain standard. If it doesn't meet a specific requirement, that means your power quality is too poor, and you need more filtering in the system, like with passive components or active components or what have you. Now let's move into the world of tomorrow, which is DC. That means everything is either coming through a battery or through a solar panel. So it's DC. That means it has no alternating current. It's a simple current that circulates back and forth in the system. Here is the DC that we expect for tomorrow. It's also wobbly. That means it's got distortion to it because it's been converted from AC to DC, DC to AC, AC to DC, back and so on and so forth. So when you measure this noise on a DC link, that's what EMC in DC actually is. That means it's a noisy DC link with a noisy current, which results in a noisy voltage coming in from Denmark to the UK, or from UK to France, or from France to Germany, or wherever you see. That's what EMC in DC actually is. So this usually happens because of interactions between AC and DC converters. That means you can have inverters produce something, and then you have the rectifiers converting it back, and you consume it again in DC or AC, whichever format. The more interactions you have between AC and DC technologies in a system, the more EMC tends to promote. Okay. And the interactions also happen because of semiconductors. Of course, semiconductors are the main things why we have EMC in DC. Then you have more passive components in the system because of resonances that happen within say capacitors and inductors connected, or STATCOMs or SVCs connected together, so on and so forth. Then you have passive filters, active filters, and all of these systems lead to EMC in the HVDC link. So we are now trying to research how to reduce noise or EMC within the DC grid, right? Okay, so a part of my research is how do you solve EMC in HVDC? The basic answer is, which I will give in this presentation, is by understanding what noise each and every power converter creates. So suppose you have a small electrical grid, like something between your house and your car. So it can have a very small high voltage or a medium voltage or a low voltage DC grid. And when that DC grid connects your car to the rectifier to the inverter in your home, there are links between which promote DC currents. So now we have to understand what kind of noise every converter in your car creates, and then measure it and see if that can be applied for a pre-compliance testing. You can use a similar logic towards understanding high voltage DC systems. So suppose the grid operators in Denmark, before they sell electricity to the UK, they will say, okay, we are now sending you electricity with just this many kilowatts, or this many for this much time, over this much potential at this voltage level. And this is the distortion index it has. That means this is the power quality it will have when we deliver it to you to the shores of the UK. So for that, you sort of need a pre-compliance EMC testing. And one of the pillars of my research is to develop novel framework to understand DC and test products. So suppose you have AC technologies like a bulb in AC. Everything about that total harmonic, everything about power quality in AC is quite well understood, but in DC it is yet unexplored. So my research takes the same principles for total harmonic distortion of power quality in AC and tries to apply that towards DC technology. So for that we need a new framework of measuring EMC or measuring noise in DC products, and to measure and to create a new framework, you sort of need a whole new test products that are still being developed in research. Once we do that, the further step is to establish standard rules and regulations, so that whenever I buy a car, to make sure that it works well in my in my garage, or if Denmark decides to sell power to the UK, or any of those conversations happen, there are enough standards, regulations, grid codes that actually exist to make sure the delivered power quality is enough, or rather decent. And that can only happen once you have a standard. So just to re-encapsulate what my research is, suppose in our laboratory here at the Polytronics and Machine Control department, we develop a simple DC-DC converter. Suppose Ying develops a simple DC-DC converter, and she comes to me and says, Arun, I need to understand what EMC this generates, because my client wants to include that on an HVDC link, and we want to make sure the product we've developed is safe enough to be included that, and it won't destroy their system, or it won't introduce too much noise in their system. So first thing you do is you develop your DC converter, then you measure it for EMC. You measure the distortion it has, both in voltage, currents, and its own impedance. You redesign it, lower the EMC by using principles of EMC, which are a bit too, I won't be going into understanding the principles for EMC, because the presentation then will become 1 hour long. So you basically take a new converter, develop it, lower the EMC, and you try to achieve pre-compliance for the first time, and then you apply that converter onto these STATCOMs or these HVDC links that you see, that even Yuchao spoke about in the previous presentation. So once you understand how to make a converter, you comply it for EMC, and then introduce it as one of the components in your HVDC grid, or as a STATCOM, or in connection with a synchronous generator, or what have you. So that's how you solve EMC in HVDC. Okay. But the problem with this is, which is what my research tries to understand, is of course you measure your converter for EMC, but you now want to understand what is lower EMC, like how much noise should I suppress in my converter to really understand what is acceptable and what is not. So when you lower the EMC and you say, okay, I want to have a pre-compliance test, I'm not sure what standard to look at it. So we have the standards for DC EMC, which require you to understand. Now, this is all research that we want to undertake here at Nottingham University and with other universities in the cohorts. You have time and frequency analysis windows that need to be understood. You have bandwidth of measurement, which also needs to be understood. Like if you have a silicon-based converter, so silicon-based usually will switch at 10 kilohertz or somewhere around that frequency. You have a silicon carbide-based inductor or silicon carbide-based converter that will start to switch around 100 kilohertz or 50 kilohertz or so. You have a gallium nitride based semiconductor based converter that's actually going to switch in megahertz. So what's the bandwidth of noise we should actually consider? This was not a problem with AC because AC is at 50 hertz. DC is open, so we have a huge bandwidth of noise that we actually want to measure. Again, once you understand the bandwidth, then you know what power quality to expect. Say if my converter is too noisy at 10 kilohertz, I know how to suppress it. And if my converter is too noisy at 50 kilohertz, I also know how to suppress that with using a very different set of passive components. Then, of course, now when you want to trade electricity, you need some sort of metric. Like when we develop electricity, we want to have a certain amount of electrical pressure, which we call voltage. And when we want to trade electricity, we say, okay, I will sell this many kilowatt hours to you at this level of power quality. We also know total harmonic distortion in AC, but we don't know that in DC. So that has to be invented yet for DC and then be applied to HVDC links. And there are other topics in EMC, like what should be the voltage grade, what should be the current grade, what impedances should the converter offer, so on and so forth. But one of the main pioneers is the first thing we want to do, which is what my PhD and my consequent research looks at, is developing a framework to understand what kind of noise every converter should make, whether you apply it for HVDC, whether you apply it for MVDC, whether it's a 6 pulse converter, 12 pulse converter, 24 pulse converter, what have you. We have to first understand what creates the noise. And for that, there's a framework of understanding that my thesis or my research does. And it's called, basically it's called a line impedance stabilization network. It's an artificial means network to know whatever converter you put across this framework, it's only going to measure the noise coming in from that converter in a way that it isolates the noise coming from the new converter that is to be measured against the grid noise that already exists in all our grids. So my research looks at developing frameworks to understand DC-based EMC. Okay, so the conclusions of my research, or rather this presentation, are there's a lot of growing research for EMC in power electronics. We haven't looked at EMC in power electronics at all. Even if we used to look, it was quite from a standard or a point of view that was from the early 2000s. But since then, we've changed our semiconductors from silicon to silicon carbide and now to gallium nitride. So everything now has to be revised over and over again. Because of that, we also need new standards, regulation, and novel equipment, which doesn't exist yet. So there's a lot of industrial and commercial opportunities in EMC as well. And there is one thing that I would like to change with EMC or with power electronics, or even here at the University of Nottingham, is that we start introducing graduate and undergraduate courses about EMC for students who are enrolled in power electronics or electrical engineering in general. We need to start educating them about EMC. I myself understood EMC when I came to the PhD. Before PhD, I also never studied EMC. Noise was something like a black box. You use if your system is too noisy, you simply put a capacitor across it and then it takes the noise away. But EMC is a whole new science that has to be understood. And I would like the new students or the new generation to understand it from graduate and undergraduate levels about EMC. Yeah. So in the end, my research may pioneer a framework to understand EMC in HVDC links that can be applied in power electronics, that may be applied to also to HVDC links as well. Okay. Yes, thank you. That's my presentation. I'm ready for your questions, if any.
Yeah, thank you, Arun. Thank you for
I'll
your
stop.
clear presentation. I believe all our audience will get a lot from it. It's very basic one for us to understand and learn why it is more important nowadays. Let's see if there are any questions for you from either our presenters and the audience.
Any questions are okay, because EMC is so new that it's sometimes not understood. So I'm willing. Yes, Mr. Yuchao, go on.
Hi, Arun. Thank you very much for your presentation. It's really interesting. So there's one topic I'm interested in is like, so for example, as our partner, what is growing, so we are trying to integrate like different renewable energies, and we have like multiple converters connect on the whole network system. So what do you think about the EMC? Do you think they will like propagate or affect each other, so coupling each other?
Well, thank you for this question. There's a lot of research about that happening as well. In fact, I wrote one conference paper in 2022, and it was about the impedance interactions between different converters. So suppose now, let me give you a hypothetical understanding of this. Suppose you're charging your car, you own a Tesla, and you're charging your car at your house. So now you have the converters operating at say 100 volts DC, and you have 10 converters in your car, and you got 4 converters in your solar panel. So on each side you have 4 converters on the solar panel, 10 converters in your car somehow, and there's a DC link that happens between them, which is a capacitor or a capacitor with a resistor next to in series to it. So all the emission from both of these sides tends to circulate in the system, and it will not just circulate within the DC link, it can also circulate outside of it. So a lot of circulation happens because of the impedance interactions. So it's more to do with what kind of impedance your converter offers before you can, or what amount of impedance your DC link offers, so that you protect your Tesla from your solar panels. So it's that kind of an understanding that has to be understood in a very layman term. Yeah.
Cool. Thank you. Thank you very much for your answers. It's much clear now.
Yes, thank you.
Thank you. Nagham, you have questions?
Yes, it's comment slash question. I'm looking at the EMC and I'm remembering, based on the communication background that I've got, we've got exactly the same problem. We don't know that much about the noise. For example, I'm aware that Ofcom, the regulator for the wireless communication in UK, they are working on a big project and they are trying to understand the noise and create the noise, because for us the noise always is a low frequency, and what we do is just we will filter it and that's it, get rid of it. We don't understand it, we don't have any that much information about it. So it's a very unique project, and what they did is just they tried to just kind of simulate and also do some practical. So my question to you, what is your strategy? What is your method just to analyze the EMC? Are you also doing like them, trying to just kind of create your own EMC and try to analyze it, or maybe this is something that you will do later on?
Well, yeah, thank you for that question, Nagham. Well, the simplest answer is one size does not fit all. Like there is a very different EMI for wireless and power communications, and very different one for PLC. Then there is one very different EMC analysis for power electronics, and then there is one very different for AC electrical currents. So suppose if I was to collaborate with you, and I hope that happens, and you say, Arun, I need something to understand PLC. So I will give you a very specific analysis of how to understand PLC, because PLC happens in a particular bandwidth, and we will need to understand EMI only in that bandwidth. Beyond that bandwidth, if there is AC currents, we neglect that. If there is say high voltage DC, high frequency DC, we neglect that. We only focus on the bandwidth of PLC. Tomorrow, if you say I'm operating in wireless communication, which happens in gigahertz, so I will then give you a very strong filter, so that all the emission from your power electronic converters is suppressed, so that we can only understand EMC from your high frequency wireless communication. So there is no one fit answer. EMC has to be applied into power electronics or any other topic. So EMC is rather all encompassing. So once we understand the problem, then we generate a very specific EMC solution for it. That would be, so there is, the basic answer is one size does not fit all. Yeah.
Yes, and you mentioned it before, and just thank you very much for your presentation. Thanks.
Thank you. Yeah.
Thank you, Nagham. Thank you, Arun. So I think that's our second presentation from Dr. Arun. If you have any further question, please type it in our chat box, and Arun will also be happy to answer it from there. Thank you, Arun.
Thank you very much. Thank you.
Let's welcome Dr. Nagham Saeed to close today's event. Over to you, Nagham.
Thank you. Thank you very much. Thank you very much, Ying. I'm Dr. Nagham Saeed, the former chair of the IEEE Women in Engineering United Kingdom and Ireland, and the IEEE United Kingdom and Ireland vice chair. Our initiatives at the Women in Engineering affinity groups are dedicated to advancing women in technology and fostering a culture of diversity and inclusion. We collaborate to enhance early profession outreach, supporting both undergraduate and postgraduate students in engineering and computing and research graduate. I extend my heartfelt gratitude to all of you who participate in the 13 Early Career Talks webinar. This webinar is a unique experience that allowed us to listen to these distinct talks on recent technology advancement and research and regulation, focusing on offshore renewable energy. Our esteemed speakers are not only from United Kingdom and Ireland, but also we have a speaker from United Arab Emirates. Hopefully you will listen to his recording when we upload this webinar on our website. Their insights have enriched our understanding of cutting-edge development in our field. Those who missed the talk live, as I said, fear not, the record session will be available on the Ambassador YouTube channel and the IEEE United Kingdom chapter section web chair. Special shout out to our sponsors who unwavering support made this event possible. This is the IEEE United Kingdom and Ireland section, the Industrial IoT Research Group at the University of West London, Society of Social Implication of Technology, Aerospace and Electronic Systems Society, Instrumentation and Measurement Society, Power and Engineering Society, Circuit and Systems Society, Systems Man and Cybernetic Chapter, Joint Chapter on Control and Communication, Computer Society, the Electric and Electrical Installation Society, and the EDI Committee. To you, Ying and Yao, thank you for your invaluable contribution to organize this event. As we move forward, we remind all of you our commitment to empower women in engineering and computing. So our next Early Career Talk event is scheduled for next year, March. So please keep your eye out for the update. Additionally, we're going to have many coming events until the end of this year. So please join if you can. One of the events that we're going to hold on the 13th of September is the Early Development Day in Queen Mary University of London, which is titled IEEE, which is supported by the IEEE Intelligent Transportation System. And the title is The Career Path to Net Zero. And it is a full day technical workshop in London. And it is organized by the Women in Engineering and the IEEE Intelligent Transportation System Society. And it will feature poster competition and targeting graduate students and early career researchers in the UK and Ireland, with the 3 prizes awards for the 3 best posters. So please keep your eye open, and we would like to welcome you in all our events. Thank you very much, and wish to see you in our coming events. Bye. Thank you.
Bye. Thank you.
Bye.
Thanks.
Bye-bye. Thank you very much. Bye-bye.
You're welcome.
Bye.
Arun, before you go, if